Welcome, Alex Young. Dr. C. Alex Young is the Associate Director for Science in the Heliophysics Science Division at NASA's Goddard Space Flight Center. In this role, he is responsible for overseeing and coordinating the education and public outreach team for the division. He works with the EPO teams as a liaison with the NASA Offices of Education and Communication. In addition, he works with the division scientists to promote and support their research. He joined the NASA ESA SOHO mission after graduate school at the University of New Hampshire as a solar astrophysicist with the Extreme-Ultraviolet Imaging Telescope. Working in this area grew his interest in image processing, which he combined with his love of statistics and data analysis. It was this, with the help of some of his colleagues, that led to his establishment of the Solar Imaging Processing Workshops, or SIPWork. Over the past 7 years, Young has helped organize and run 5 workshops and edited 3 special topic solar physics journal volumes on solar image processing. Part of what he enjoys about data analysis topics is the sharing of knowledge with the solar and astrophysics communities. This has led to his participation with the California-Harvard Astrostatistics collaboration. Ladies and gentlemen, Dr. C. Alex Young.
Hello, I'm C. Alex Young, the Associate Director for Science in the Heliophysics Science Division at NASA's Goddard Space Flight Center. I'm sorry we can't be in person, but I'm excited to be able to give you this presentation virtually. Today, I'm going to talk about the Parker Solar Probe and arguably a new golden age of solar physics. You know, the sun that we see every day can be beautiful, or more likely its effects can be beautiful, sunrises and sunsets, but it's not too exciting of an object. And in fact, it's actually really too difficult to look at. It's so bright that we can't look at it with our own eyes. We have to use safety glasses, the same kind you use during a solar eclipse. If you take a picture with a regular camera, again, you just get this washed out image because it's just such a bright object. But it is, of course, our source for heat and light and very important to us. But there's a lot more going on. And on the Earth, with special telescopes, you can see a little bit more of what's interesting with the sun. But it turns out that during one special time, a total solar eclipse, we can actually see some amazing structure and see amazing dynamics in the sun's outer atmosphere, what we call the corona or crown. During a total solar eclipse, when the alignment of the Moon-Sun-Earth system is just right, the Moon nearly completely blocks out the sun's disk, its bright disk called the photosphere, and the outer atmosphere, the corona, millions of times fainter, now becomes opened up to our eyes. And in fact, we see structures, loops. These are caused by magnetic fields on the sun. You see these pink structures, which are actually pieces of the sun's lower atmosphere supported by magnetic fields up in the corona. And so total solar eclipses have been one of the first ways that scientists have begun to see the excitement and the interesting things happening in the sun's outer atmosphere. But we do have some amazing, powerful telescopes on the ground, but there are some types of light that we can't see here on Earth. Now, this is visible light, but types of light that's much more energetic, ultraviolet, the kind of light that gives us sunburns, or extreme ultraviolet, even X-rays and gamma rays, mostly doesn't make it through our atmosphere, which is great for us because it's not particularly good for our bodies, but that also means that we don't see the sun in these wavelengths of light, and we're missing a lot of interesting physics, a lot of interesting dynamics. So one of the things we do is we put a spacecraft with solar telescopes into orbit above the atmosphere, and this allows us to finally see a very different, unique sun. Here's a look at the sun in extreme ultraviolet, several wavelengths of light, much more energetic than visible light, light we can't see with our own eyes. And look at all the activity. You see that flash, that's what's called a solar flare, a flash of light covering the entire electromagnetic spectrum with enough energy to power the world for 100,000 years. And you see all these structures wiggling, and in fact, after that flash, you see material moving, and in fact, billions of tons of solar material are blasted into space, eventually filling the whole solar system. This stuff travels at millions of miles an hour. It carries the sun's magnetic field with it. And this type of energy and matter creates an incredibly complicated environment in the solar system driven by the sun. And in fact, as you go higher up in the sun's atmosphere, you see more and more structure when you look at higher and higher temperatures. These are more energetic wavelengths of light. So as we go to ultraviolet, extreme ultraviolet, and an X-ray, each one of these is moving higher and higher up in the atmosphere, and in fact showing us a higher and higher temperatures. The sun's surface is about 10,000 degrees Fahrenheit, but it quickly moves up to many millions of degrees as we move into the corona, this part of the atmosphere that we can see during a total solar eclipse. So this is one of the amazing discoveries and challenges for solar physicists. Why does the atmosphere get hotter as you move away from it? It certainly doesn't make sense when we think about a campfire. As I move away from the heat source of the campfire, it gets cooler, and that's not what's happening on the sun. But also, this atmosphere that's getting hotter and hotter escapes and streams away into space. Particles and magnetic field streaming away from the sun create what we call the solar wind. This solar wind and these huge eruptions of material we call coronal mass ejections, those flashes of light called solar flares, create an incredibly complicated environment, and in fact they create their own weather in space, what we call space weather. And all of that solar wind, as it expands out, we see in this animation of the solar system, creates this complicated bubble around the whole solar system. And that bubble is elongated as it's traveling through interstellar space. As those two interact, it creates a wake, like a ship traveling through the water. And you see this bubble moving in and out, almost breathing, and that's as the sun's activity increases, the bubble streams gets bigger, and as the activity decreases, it shrinks. This is happening over roughly an 11-year period called the sun's activity cycle. And all of that energy and matter is interacting with everything in the solar system, including our own atmosphere. And in fact, the solar wind and these solar storms, coronal mass ejections, interact with our magnetic field here on Earth and our atmosphere and create the northern and southern lights, the aurora borealis and the aurora australis. Here's an image of the southern lights from the International Space Station, the ISS, over the Indian Ocean. This is one of the first signs we have of this space weather interaction. And we're living in the atmosphere of a star. All of this material flowing out is creating this environment, and it's in fact the extended atmosphere of the sun. Here is a data visualization showing you particles from the solar wind, and in fact this giant, huge cluster of particles from a coronal mass ejection. As they pass by the Earth, you can in fact see that the particles are moving around the Earth because some of them are being deflected by the Earth's magnetic field. It's acting as a shield, and these particles, which react to magnetism and electricity, move around it. Well, back in the 1958, we launched one of our first rockets, the beginning of the space age, into what's now called the Van Allen radiation belts. A rocket with a Geiger counter sending up a spacecraft headed by the team led by James Van Allen showed us the first glimpses that space was not empty. In fact, it was radioactive, full of all of these particles and energy. And scientists at that time decided that there were many questions that we needed to answer. So they put together a bucket list. And this bucket list had all of these different achievements we wanted to make, one of which was to send a spacecraft to the sun. And in fact, around that same time, a young scientist named Eugene Parker theorized that this expanding atmosphere of the sun created what we call the solar wind. This was something that at the time we didn't know about, and Parker theoretically predicted that it existed. And in fact, a few years later, we discovered for the first time real data validating this theory that was once maligned by many scientists as not being realistic. And so this led to the beginning of the works of Eugene Parker, who provided incredible science and insight into the workings of the sun and how it interacts with the solar system, what we call the whole field of heliophysics. And in fact, some of the same physics applies to stars outside of our own solar system. But one of the big questions is, why hadn't we gone to the sun yet? Well, the main reason is technology. And within the last 10 years, a project called the Solar Probe Plus was in development because we finally had made these technological leaps. So going from 1958 to now, the technology needed for the solar probe to become a reality was like a leap from a rotary phone to an iPhone 10 or an iPhone 11. So this was a monumental step in technology. One of the big issues was thermal protection, heat. The sun is really intense, and as you get very close to it, the heat that the spacecraft experiences is extreme. You can imagine going out on a really hot day, how hot the sun is. Well, imagine if you are much, much closer, if you are feeling the much more intense sun. And in fact, on its closest approach, the heat shield would experience a temperature of 2,500 degrees Fahrenheit or 1,400 degrees Celsius. So scientists and engineers developed a heat shield made of carbon foam, carbon fiber composite that protects all of the instruments. They all sit behind it except for one of them made from special material to handle the intense heat. And the only other thing that sticks out are the solar panels, which I'll mention in a second. But just to give you an idea, if you look up in the sky, the moon is about a half a degree in the sky, the apparent size, and the sun is equivalent to this roughly. And when we get to the location that the solar probe is getting to, much, much closer, the sun actually is 14 degrees in size. So around 28 times bigger. And in fact, the the intensity is about 500 times more intense. Incredibly huge amount of light, and that light hits the front of the spacecraft and heats it up. So while we're close to the sun, we have solar arrays, which is great because we have a lot of sunlight. But the problem is the heat is so intense, and solar arrays are made out of the same kinds of materials in electronics, and they don't like heat. You might have maybe seen a time when you had your phone in the sun, it got hot and shut off. Well, that's because electronics don't like high temperatures. And so in order to deal with this, engineers created a very intricate cooling system or radiator. And in fact, it was so amazingly developed, it only needed 1 gallon of regular water to cool the solar arrays. And so on the closest approach, they fold in and they are protected from the heat by a combination of the heat shield and the solar arrays cooling system. So how close is the solar probe going to get? Well, here's the sun on a 100-yard line. On one end is the sun, the other end is the Earth. Venus would be at the Earth's 28-yard line, Mercury at the 35. So the solar atmosphere that we're interested in seeing extends out to about the 15-yard line. The Helios 2 spacecraft was up until now the closest spacecraft, reaching the 29-yard line. Now, the Parker Solar Probe is actually going to make it to the 4-yard line, basically within 4%, well within this region of the sun's atmosphere. Now, one of the things I didn't mention is originally we called it the Solar Probe Plus, but the spacecraft was named after Parker, the gentleman who discovered the solar wind. And in fact, this is the first spacecraft to be named after a person who's still alive. And in fact, in August 2018, when we launched the Parker Solar Probe, Eugene Parker, his wife and son were at the launch and were able to see the culmination of all his research over the years as the spacecraft was launched on its voyage to come within roughly 3.5 to 4 million miles from the sun's surface. Here's an animation showing the orbit. So it's launched from the Earth, and each flyby around, it's making 24 orbits. On 7 of those orbits, it flies by Venus, which gives it a kick, a gravitational assist, allowing it to get closer and closer so they can make its closest approach. Here's a look at its first and last flyby. The first perihelion, its first approach to the sun, has already been made. It's now made 3 of these visits, and you can see where it actually encounters Venus on some of its orbits, 7 of these orbits. So on its first perihelion, as we call it, closest approach to the sun, it's actually just under 36 solar radiuses, and on its final on its closest approach, the minimum perihelion, it's 8.86, just under 9 solar radiuses. And so October 29th in 2018, it made its closest approach, that's 26.5 million miles. And at that point, it was the fastest spacecraft ever, traveling at over 150,000 miles per hour. When it makes its closest approach, which will be in 2024 on a 24th orbit, it'll be traveling approximately 430,000 miles per hour. That's fast enough to go from Philadelphia to Washington, D.C. in 1 second. Less than 4 million miles. So one of the amazing things about the timing of the Parker Solar Probe is not only is it the culmination of 60 years of science and 60 years of technology development, but it also corresponds to some other missions and telescopes which are giving us a first unique look at the sun. So over the past many years, scientists have been building, with the support of the National Science Foundation, the Inouye Solar Telescope in Hawaii. And this is providing unique views, high resolution views of the sun in visible light, allowing us to see the sun's visible surface, the photosphere, with detail never before seen. We can see structures down to the size of what are called granules. These are where solar material bubbles up to the surface, much like a pot of bubbling water. And these bubbles, or granulation cells, are roughly the size of Texas. They're about 4,000 miles across, or 7,000 kilometers roughly. And you can even see structures within them that's about the size of Manhattan. There's a Manhattan skyline. But in addition, we also were able to launch a new mission with the support of our partners at the European Space Agency, a mission that they built, which NASA launched and provided some instrumentation, called the Solar Orbiter. And this mission supplements and complements the work of Parker Solar Probe. While it doesn't travel as close to the sun as Parker Solar Probe, it looks at what's happening after things pass Parker Solar Probe and start traveling out into the inner solar system. But also, its orbit is not in the plane of the solar system, but in fact it moves out of the plane of the solar system, roughly 30 degrees of an angle. And this is giving us a first ever view of the poles of the sun, the North and South Pole. These are areas where we don't have any data, but we know these areas are very important to understand what drives the sun, the magnetic fields that are driving the sun. And this is giving us the opportunity to really understand the bigger picture of what's happening. So we now have the Inouye telescope giving us details of the solar disk as the Parker Solar Probe is traveling closer and closer to look very, very close to the sun's surface in the sun's corona, and then having the Solar Orbiter spacecraft to give us views in the inner solar system as well as views from the pole. Together, these are bringing us into a new age of solar physics that we can finally start to understand why the sun is active, how its magnetic field drives space weather, how it drives solar eruptions, flares, coronal mass ejections, the solar wind, and ultimately to help us understand how those events can be possibly predicted and forecast like weather we have here on Earth, because not only do they give us the beautiful northern and southern lights, but in fact they impact our technology, they impact our ability to communicate, they disrupt our spacecraft, and they can even create a hazardous environment for our astronauts in low Earth orbit and as they travel to the moon and eventually beyond to Mars. Understanding space weather helps us protect our local infrastructure, our technology, as well as improving our ability to explore our solar system. Thank you very much. You can find out more about Parker Solar Probe at the Johns Hopkins Applied Physics Lab. You can follow NASA on Facebook at NASA Sun Science. Also, my Twitter is @TheSunToday, and NASA Sun is the other Twitter account. And you can find out more about Parker Solar Probe and Solar Orbiter at my own website, thesuntoday.org, or send me an email, c.alex.young@nasa.gov. Thank you, and I hope you enjoy the rest of the NEAF 2020 virtual conference.